So I am Aristides Marcano, professor of physics at Delaware State University. And we work actually in the Division of Physics, Engineering, Mathematics, and Computer Science. They put us together, so they make this big division on science right now in the university. We're located in Dover, Delaware. So most of the people don't know where is Dover. So I have this, because it's a very tiny state. It's the second smallest state, no? But you see where is New Jersey, which is nearby New York. So the south of New Jersey, you can see in the screen that city of Dover, where we're located, is a tiny state. But of course, the current president of the US is from Delaware. So Joe Biden is a very well-known senator from Delaware all time, and now president of the US. So Dover is a small town. So here's a map of the state of Delaware. You can actually see it's the south of New Jersey. This is going to be the west of the east of Maryland, and the north of, there's just in the south we also have Maryland again, and then some part of Pennsylvania and this in the north. But anyway, Dover is well known because we have an air base there, a big air base, which is bigger than the town, and then on the top we have a photograph of the legislative power there we have in the city, because it's the capital city. So Dover is called the capital of the first state. The first, Delaware is considered the first state because it was the first state who ratified the US Constitution more than 250 years ago. It was the first to sign that document. And this is a photograph of our campus. We have a big campus. This is actually an historical black college. It was created 130 years ago for education of black people, in the sense what they call that colored students at that time. But today is not that. Is the reality is that we have a very diverse school. We still keep a lot of African American students, but we have students from, we have a lot of Hispanic students, we have a lot of white students, and we have a lot of foreign students that actually make our school very diverse and very interesting. And then on the right, you will see a photograph of our center, which is a building that was completed in the 1960s. And still, it's an old building, but it's still in good shape. And my lab is somewhere in the second floor. I have a nice lab there where I do the experiments. Anyway, just talking about photothermal in general, and that refers to the light-matter interaction to the generation of heat. So anytime you have an absorption of heat, you have an interaction between light and matter, there is some heat being released, and that follows the absorption of light photons. And that heat produces some changes in matter, and that changes can be actually understood as changes in the susceptibility of matter, or refraction index and absorption coefficient, and that affect the propagation of light. And that's what we call that the photothermal effects. So it's the effect of light produced by the light itself because of heating in matter. And the thing is that here you have several examples of photothermal effects, very well known, and the most popular, and I have that. One is the photothermal refraction. When you have one surface, could be a metallic surface, you just focus their pump laser, represented by this green. We usually have a green laser for that. And then we just send a test laser, a probe laser, and see that that probe laser can be deflected. No? And sometimes there's some deflection, and people develop that method because it's very sensitive, and it has that the deflection is due to the gradient of the refraction index that happens in the nearby region of the surface. You can have a photothermal reflection. And it means that you actually create some kind of changes in the reflection capabilities of your media, and then using a pump laser because of the heating, for example, you can make some distortion of the sample, so create some kind of bump over the surface, and then that bump will actually reflect the light differently, and you can see these effects on the far field, and have that. There is the other thing we do is the photothermal diffraction. So we say diffraction where they have some something is hitting or something is blocking the light somehow, but this is not actually blocking. It's just we have some changes in the refraction index inside because of the heating. And that's represented by this concave parabola right here. Is mostly represent that the refraction index decreases, no, with the temperature, and close to the center where you have more intensity, you have less refraction index. So it's like a lens, as we call that. In this case, in liquids, this lens actually is the focusing, and you can actually see that the focusing effect, in particular, in the diffraction pattern of the far field. And these methods are very sensitive. There are other effects. Actually, you can do photothermal interference. You can do photothermal or photothermal absorption and something like that, nonlinear. Other different effects. I think you can actually check different ideas in this book. Actually, this is a recent edition of that book. Interesting, it's quite international because Stephen Balkovsky is a well-known professor from Utah. He's an American professor, and he started with this book about 20 years ago, in the 1990s, and then he did this new edition because the book is very popular among the people working in photothermal method, and he also worked with this professor from Brazil, Nelson Astrat, and also a professor from Russia, it's Mikhail Praskurin, and that Praskurin. I think these are a very international team, and they make this updated version of that method. I think it's a good book. You can actually get over Amazon. Amazon is not paying me any money for that, so I don't think I am doing some ad for Amazon. But anyway, well, the major characteristic of the photothermal effects, you can find a lot, but I think there are two of them that are very particular of photothermal effects, is the universality and the sensitivity. So the universality actually is just an expression of the second law of thermodynamics, is that any interaction, when you just inject energy into matter, that energy at the end, after relaxation processes, becomes heat. So you are just injecting some heat into matter. That heat is coming from the energy from the photons. And I have that. And that happens all the time. You have any interaction, any kind of interaction, you will have this degradation of the energy into heat, and that heat remains that sample for a long time. And I have that. And that what makes this characteristic that whatever happens, whatever you do an experiment, you will always have these photothermal effects. And maybe if you have too much scattering, maybe it's not that important, but you're still there. So you cannot remove that from the interaction. And the other point is that the sensitivity. So the sensitivity of this method is particularly high. And that's something was very unexpected at the beginning. So the people actually, Professor Balkovsky actually, he's an analytical chemist. Actually, they discovered that using this method, you can detect very small amount of pollution, of pollutants inside the sample, and you can use that for analytical chemistry and do some interesting analysis with very sensitive analysis of the sample. So we're going to just discuss. First one, I just got this from the internet, just saying that you have some interaction, wherever it is, with matter, light-matter interaction, could be very complex. In particular, you have high intensity. But anyway, there is always some release of heat. You can actually have that all this heat is coming from the different relaxation processes that happens in matter. And you know, so these relaxation processes, they happen very fast, usually, but the heat remains there for a long time. And that makes the point for the second characteristic. It's about the sensitivity of the method. Here I did this calculation a long time, some few years ago. And you see that, imagine that you have 1 microliter of water, 1 microliter of water, just when you see a lot smaller than 1 milliliter, no, 1,000 of a milliliter, just a tiny drop of water. And then you have only 1 atom. So imagine that the water molecules, they don't absorb the light. They are just has a very low absorption coefficient. But imagine that you have 1 atom, 1 single atom there in this capture, in this microliter water. And then you illuminate that microliter with some light that is being absorbed by this atom because of the resonance effect. And then you can actually see that what is happening is, so the atom is going to absorb that light, and then it will release the energy. It gets excited, and then it releases the energy toward the surrounded water molecules. And you can estimate the surrounding water molecule will be over 10 to 20, it's a lot, around that, compared to one single atom. And then you will see that around this atom will be there will be happen that release of heat toward these solvent molecules, and I have that. The point is that that process of relaxation is very fast. So usually that atom releases that energy in a time frame of 10 to minus 10, 10 to minus 13. So I'm talking about something picoseconds, femtoseconds, even femtoseconds. You can actually see that that happens very, very fast. It means that that heat will be there, but that the heat can move, of course, because of these diffusion effects, that thermal diffusion effects. They will remove that heat somehow, but that process is very slow. It takes seconds, milliseconds to seconds to equilibrate, to get the temperature equilibrium in this microliter of water. And it's going to take too long to get the equilibrium there. It means that that single atom can accumulate the energy of 10 to 8, 10 to 13, so trillions, trillions of photons. It means that you just on one single atom works like he's absorbing the energy for 1 trillion photons. And that's the basic thing that makes that method very sensitive. And the point is that this single microliter water will raise the temperature, the average temperature, by 1/1000th of a degree. As we will see, this is good enough that we can detect this kind of changes in the temperature. Even with, you don't need a sensitive thermometer, but you detect that using this photothermal method we're going to talk about. So that's a very simple calculation. I recommend you to do it, and that will be cool to show that that is the basic thing for the sensitivity. But there is another point. There is another point for sensitivity, is that usually what you create in your sample, you generate some changes in the refraction index. And these are phase changes. There's a phase changes just because the refraction index changes with the temperature. So here you have this dNdt, this characteristic. So usually this dNdt, the gradient of the refraction index, is very small, 10 to minus 4, and the delta t is 10 to minus 7, 10 to minus 3. So it gives you a factor of 10 to minus 7, but you can actually recover that factor because just looking at the next number, which is the length of the sample divided over the wavelength. So the length of the sample could be a few centimeters, maybe millimeters, but still lambda is in 500 nanometers. It's very small compared to that. So you can actually see that you can create changes in phase that are significant for our experiment. And I have that. That's a phase experiment, similar to interferometry. For a long time, people believe the interferometry is the top of the experiments, is the most sensitive experiments you can do. You know that it's being used for detection of gravitational wave, the idea of the interferometer of Michelson. But actually, I have worked. We work with some people doing this interferometry back in Venezuela, Professor Escalona. And he actually didn't believe that photothermal method is so sensitive. And I told him that the sensitivity is similar to interferometry because it's a phase method. He didn't believe that, and he tried to demonstrate that photothermal lensing is less sensitive, but he discovered that it's not. They are more or less, they exhibit the same sensitivity, and we make an excellent paper about that together with him. He was very suspicious about this photothermal lensing, but we just demonstrated that it's similar to interferometry in this case. Anyway, so we have this photothermal lens effect. So we create some changes inside the refraction index because of the temperature. And that changes produces some field. There's a field of the refraction index, which can be understood as a lens. And that is like having some kind of phase plate. So you have a field represented by the letter E, so an electrical field, after passing through your sample that has a length L, you can actually have imprinted that phase there. So you're making some kind of phase plate effect. And you have that phase plate, as I told you, is proportional to the changes in the refraction index, which are proportional to the temperature. So the temperature changes induced by the absorption. So the base of the theory, the basic of the theory, is just a very well-known problem of mathematical physics. Is called how the absorption produces a distribution of temperature. What is the distribution of temperature produced after absorption of what, or absorption of light? When you have that, you can actually, to calculate the induced phase, we just need to calculate first that temperature gradients that is generated thanks to the absorption of the beam. So for the simplicity, people use Gaussian beams. And you can use any beam, because any beam, but the point is that any beam will create a Gaussian process, because the diffusion process is fundamentally a Gaussian process, so you will have more or less the same effect. But you can do it simply, you can do the calculation easy when you consider Gaussian beams. Good, you do that, that's the equation that you have. This is the Laplace equation, very well-known equation, yes, established in the 19th century. And actually, people solve that equation in different conditions, and they have plenty of different papers published about how to solve this in differential equations in four dimensions. And I have that because you have this Laplacian right here, no? Which is the Laplace operator squared. That's the Laplacian, which is dependent on the coordinates x, y, and z, but also you have your time dependence, and have that is the typical problem of mathematical physics. And then you have your inhomogeneous part, which is given by this absorption, the absorption of light represented by this watts, or this intensity of light, W. And the absorption is proportional to the absorption. And of course, there is some coefficients. And of course, the time evolution is given by the thermal diffusivity coefficient. So you have very slow thermal diffusivity, you will concentrate more the heat. If you have very fast thermal diffusivity, you will cool down faster, and have that. Okay, that's the basic equation. So this equation has been solved by a number of authors, and I think they're excellent papers. I think one excellent paper is by Winery. I don't know if I left that paper here, but we did it too. We actually calculated ourselves in one of our papers, and we actually got the solution of this temperature field. And I think everybody working in thermal lensing actually need to start with that calculation of the temperature. And see, you get this equation, which looks very impressive. It's an elliptical integral, and I have that. It cannot be calculated by hand. No, it's not an easy function, but you can calculate it using any program. I use a program called MathCAD, and it gives you your solution in milliseconds. It's very easy to solve that problem using the computer programs we have today. So the important thing here is just we have this temperature amplitude. That temperature amplitude is given if you have a continuous light there. So you will have it's proportional to the power of the light, P sub 0, and also to the absorption. So, but this absorption is, we can consider that this is not the actually loss in the sample, because the sample can have some scattering, it can have some fluorescence, some phosphorescence, some Raman, and that effect actually impact the transmission of the sample. But I'm talking about this alpha is just the thermal absorption. It's the absorption related to the heating that produces the heating of the sample, and have that. Then you have the thermal conductivity K right here. So just has a regulation for that amplitude. So if you can calculate that amplitude, you can actually get information about the thermal conductivity. But there is also the time evolution of this equation is ruled by these coefficients called the time built up. Time thermal lensing built up is called TC, which is proportional to the radius of the beam square and inversely proportional to the diffusivity of the sample. So it means that the time evolution can give you easily the thermal diffusivity of your sample. So this can be used for determination of important characteristic of thermal characteristic of the sample. Anyway, that's a very well-known equation that can be solved easily, despite this impressive view. But anyway, that's the solution. I calculated myself using MATCAT. And you can see at the beginning, so I put that at the time 0.1 seconds, so it's 100 milliseconds. So you have a distribution of temperature that follows the Gaussian beam. So it's around that, the radius of the Gaussian beam given by this RE. It's around that. So it's just some kind of thermal photograph of your Gaussian beam. But over the time, there is some diffusion, then there's diffusivity there acting, and then that starts spreading. And also because you are pumping all the time, that will grow in amplitude. So you will grow in amplitude, and it say, what happens if I just keep the laser for forever? So you're going to just burn your sample, no? You're going to evaporate that light, that sample somehow. But anyway, you just keep it in such a way you don't change much the temperature. So in this calculation, I just did it for estimating that I have a laser of 30 milliwatts, and I use a green light, 532 nanometers, and using water, just water there, just a couple of millimeters of water, and they produce that small change in the temperature. As you can see, it's similar to the change that one single atom produces in 1 microliter of water, and I have that. Good. So you can calculate easily this temperature, and then, of course, you can calculate the phase. And then you calculate the phase. You can go, okay, we know the phase. We know the phase. If you know optics, you can calculate what happens with the beam at the far field using these diffraction approximations. Usually we use the typical classical Fresnel approximation, considering that we are looking at the distance, which is much bigger than the size of the thermal lens, and that approximation is very valid there. And you can calculate how is going to be the field. That problem has been solved too in some of our papers. I can show some of them, and you can just follow. It's a little bit complicated because it's a diffraction problem, but actually it's not. It's some kind of classical problem, so it can be done. Anyway, here you have a general pump probe experiment. I have this parameter called the M more than about 1. M is the so-called Modmatch parameter. It means that this is the difference, this is the relation between the sizes. If you are using the two beams, you are using a pump, what they call that, represented by this green light right here. And this green light represents the pump. So you are just focusing the pump over the sample. And then we are using the probe. We can actually focus the probe beam, a probe beam in red, maybe a Heine laser, for example, and any other laser of different wavelengths. And we are just sending that toward the sample, and that probe will just test the thermal lensing. So we're going to observe the probe beam only, and we're going to just block the pump. We block the pump, so we just use the pump to create the thermal lens and use the probe to test that thermal lens. And then we just put a detector, and just because of the thermal lensing, that transmission of that, we send that through some kind of aperture there, and behind the aperture we have in the detector. If we have changes due to the thermal lensing effects, because you have changes in the diffraction pattern of the far field, you will see changes in the profile of the beam, and you will have changes in the energy transmitted through this aperture, and then that changes can be actually monitored on the detector. And that's the typical thing. Of course, you can see, you can have different parameters here, so you can you can conduct different kind of experiments. No, if you take this, considering that your sample, your beam radius of the probe is similar to the beam radius of the pump, so you have that Modmatch conditions, and I have that. So I need to hurry up a little bit. Anyway, so are the advantages of the pump probe experiments. So you can demonstrate, we demonstrated that you can have higher sensitivity, very high sensitivity. You can optimize your experiment. You can do thermal time dependence experiments. You can do a spectroscopy. If you have a tunable pump source, you can do a spectroscopy. And that's the point of this presentation today. Or you can just use detection technology in the visible. So you can do infrared spectroscopy. You can do UV spectroscopy without using UV detectors or infrared detectors, which sometimes they're more expensive or more difficult. And of course, you can have a variety of different configurations possible with this experiment. But this is the configuration we actually call the optimized, because we demonstrate when you use a continuous wave light, this signal is one possibility for having the maximal signal you can get. And here's, for example, in this case, you have your pump beam being focused and the probe beam is being collimated. That's the configuration I recommend for doing the experiment if you are using continuous wave pumping. And then you just block your beam again, your pump beam again, and then you observe the changes over the probe beam using the aperture and the detector. That configuration provides you an optimized version of that. And in this case, the size of the probe beam in the focal point is much bigger. No? Much bigger, I mean thousands of times. This coefficient m, which is the square of the relation between the radius, could be about 2,000, 3,000, maybe more than that. So people just do m equal 50, but you can do very, very big. That makes sense. And that then you define your signal. So you define your signal so the energy you detect passing through the aperture when you have the thermal lens minus the energy when you do not have the thermal lens, and you divide that over the energy when you do not have the thermal lens effect, and then you define that as your signal and have that. So of course that you can calculate that. That can be calculated using the diffraction theory, but we're not going to do that in this seminar. And we just show that for that paper, you can see some details. The paper, we did that about 20 years ago. And we actually see that you can get a very simple formula for that signal. And that is very popular formula. And that is actually valid if the amplitude of F0, if the signal is very small. So if the signal is small, so that changes in the phase is very small, and talking about 10 to minus 3 radians, so even less than that, you can actually use that formula with confidence and have that. And here is the factor M, so they call the Modmatch factor, that has the relation between the radius of the beam of the probe beam divided over the beam of the radius of the pump beam, and have that. And again, we have this thermal buildup signal. So the signal will give you the time dependence of the signal will give you the diffusivity of the sample, and the amplitude of that will give you the absorption coefficient if you want, or other parameters, and you will need to that. This is the calculation you can do using this formula. If you consider that m is equal 1, it means that this is the Modmatch situation, and you get the typical. If you do a z-scan experiment, the z-scan experiment means that you move your sample around the focal point, and you will get this particular shape that will represent like the Z of Zorro. They have that. That's the reason it's called Z-scan. It's a very popular method for detection. People use this method a lot, but sometimes they get confused. And one of the confusion, why you get negative signals and have that. And plus, that's a problem of diffraction, which is difficult. It's not easy to understand, but it is coming actually from the compensation between the diffraction and the thermal defocusing and have that. Or the thermal focusing. But if you do the mode mismatch, the method we use, you get this kind of shape, which is only one single beam. It means that at the center, what you can see in the typical Z-scan, at the center, when you have the maximal intensity, you have very small signal. But in here, you have at the center, you have a maximal signal right there. It's more or less easy to understand. You should have maximal signal when you have the biggest intensity, and that is one of the reasons I recommend you. The interpretation of the experiments easier, no, when you do the mode mismatch experiment. Anyway, that's calculations. That's the reality. That's just a column of 2 millimeters of water, just simple water, clean water, distilled water, and you can actually see how the transmission changes in time. So when you do not have, you just chopping your pump, and you see when you don't have your pump, you have this level You have this level T0. This is the level of light transmitted when you don't have the thermal lens. And that TZ is the level of transmission when you have the thermal lens. You can say you can actually see that even using a small laser, even using a sample that has very low absorption, like water. And that's the real signal we calculated. And from this same experiment, you can see the evolution. The signal is negative, expected, because of the negative value of the thermal lensing effect. This is the focusing lens. You can see the time evolution of your signal. And you can get a very good fitting with the model of with that theoretic represented. You can see the signal is small. No, it's 0.03, and I have that. Good, and that's an experiment we did also more or less at the same time in water. We just showed that the sensitivity what they have. Here you have an experiment just taking the AC component of the signal. And of course, we cannot calibrate that, but we can calibrate over noise or other samples. But anyway, in the dot line represent the pump. When you have the pump, you have growing signal, which is when you have no pump, the signal grows. When you have the pump in, so the signal decreases, and I have that. You have this wave. And then we notice that you have something from the cuvette itself. So the method is so sensitive that you can get signals from the cuvette, and here you have your signal from the cuvette, which is now they are positive, but actually it can give you the evaluation of your signal to noise ratio, which is about 20 times here. So you multiply, you have a signal to noise ratio for the water experiment of 10,000. Some people say that it is difficult to believe, and it's too good to be true, but that's the real experiment we did. It's published, and we published that. That's the time evolution, real time evolution for water. You can see it's very nice. Even the signal is really small. You can actually see the time evolution very well when you do this Z-scan experiment. So what about spectroscopy? So you can do spectroscopy if you have a tunable source. And for example, this is an experiment we did with some Brazilian group back in Brazil. They invited me, and I explained then about the experiment and say you can obtain very high sensitivity. Okay, they have a argon laser, and the argon laser has different points there. And we just measured the thermal lensing for this single water. That was a paper in 2009 that we published. And they published other papers related to this. They see the stars are the thermal lensing measurement, and the others are measurements of other people. And usually in water, in the blue region, you see in the 400 nanometers, it's difficult to measure because there is some scattering. There is a scattering from water, and the scattering can affect the transmission. All the other experiments are transmission experiments. So in transmission experiments, you have the scattering. And because of that, there's some splitting apart. So it means that actually the thermal lensing can measure very, very small absorption, almost 10 to minus 3 meters minus 1 for water. And I have that. And I think we have the record at that time. But you can do also the similar experiment using, for example, these experiments were done using a femtosecond laser for what they call the middle laser, which is a titanium sapphire laser, which is very common. People work with the femtosecond, but you can work also in CW regime, that's CW regime. And actually we compare the experiments in infrared, taken from the TL spectrum, that are the squares, and the others points are the points from other people doing the experiments in transmission. Here the scattering is not important because you are in the infrared, it's not that important there. And you can see a very good coincidence in that region of the infrared. If you happens to have these kind of lasers, you can do this spectroscopy right away. And here you have, for example, an ethanol. We did a spectroscopy there too, using the same system. I tried to compare with the transmission experiments, and we got some differences, but still this paper was not finished. I didn't need to retake it because the laser was taken from me, so I was unable to finish that. Anyway, we did this experiment back in Venezuela a long time ago, and that we used an OPO, pumped by the jack. And then these experiments were able just tune, with the OPO, you can just tune in particular in the visible light, and you can actually do thermal lensing. At the same time, you can do fluorescence scattering. You collect everything that is being emitted by a sample, or it could be fluorescence, it could be scattering, and you also measure transmission in this experiment. So this is a full with the absorbance, fluorescence, photothermal spectrophotometer, and I have that. If you have a device like that, you can do these experiments right away. I will just show the important thing here, so that you have, when you do the thermal lensing, and you have, this is the square, the triangle, the black triangles are the thermal lensing result. It's very small because this sample has a very big fluorescence. And this is the absorbance fluorescence excitation spectrum that we can get, and you can have that. And then we also measure the transmission of the sample, the one minus the transmission, which is the absorbance, and because the absorption is very small. And you can actually see that if you zoom thermal lensing plus fluorescence, you get the absorbance. That means that the absorbance, what you measure in the transmission experiment, splits into some is going to fluorescence, some other is going to thermal lensing. And we can see that the thermal lensing spectrum is very different from the total transmission spectrum. You can actually estimate the fluorescence quantum yield of this experiment just using this relation between the thermal lensing and the total absorption. And we have this alpha is the total absorption. I have that, and that is the absorption of the thermal lensing. When you do that, you can actually obtain the fluorescence quantum yield, which is a number that says how is the ability of that particular sample to produce fluorescence, and have that. Anyway, if you can use quenchers just to prove quenchers to eliminate fluorescence, if you eliminate fluorescence, quantum yield, you use a quencher, you do the same experiment, you can see that your quantum yield reduces substantially. So the quenchers just kills the fluorescence. You can see that now the dominant effect will be the thermal lensing because there's less fluorescence. But we use a white light spectrophotometer. So we're just using, that's a good thing that you can actually do using a lamp. And you have a lamp, a xenon lamp we used to have there. And we use that as a pump. And this lamp, actually, we have a set of filters. I think this is the method used for my former students still. And we did this experiment also in the 2005, I think. And we focused that on the sample. And then we just send the Hini laser, the red light, the probe beam, collimated into the sample, and we observe what is happening right here. So we are able to do, even with the lamp, I'm just observing some samples there. So here, for example, here we have a sample which is rhodamine with malachite green, sorry, in ethanol. Malachite green is just a non-fluorescence dyes. There is no fluorescence. And you can see a very good, excellent agreement between thermal lensing and absorbance. So there is nothing else but heating being generated in this case. So there is an absorption of that. That was published in 2006. It's still done back in Venezuela with this experiment. But anyway, we will do a fluorescence dye. So the fluorescence dye using this light shows you different spectra. So you have, this is the PTL is the starts, and that is the absorbance spectra. So you get that the PTL is something different from the absorbance because you have a fluorescence there. We did also an experiment back in the US in 2014. I have some visitors from Mexico, and I have another student from China actually. And we did this experiment with scattering samples. We just have some dyes like this, the same malachite green oxalate, and then just we add in some latex microspheres. We add in some latex microspheres. That these microspheres, they have some scattering. If you don't have microspheres, you get a very good coincidence between thermal lensing and absorbance. So you see excellent coincidence. But if you have your microspheres, so the absorbance produces some big difference between thermal lensing and that. It means that we can actually estimate the scattering quantum yield. We can estimate the scattering quantum yield of the sample, and that's what we did. This is an experiment we did in gold nanoparticles. We are very popular because of the multitude of applications you can have. And you see these gold nanoparticles actually follow the thermal lensing very, very well. And the absorbance follows the thermal lensing. It means that for these particular nanoparticles, 50 nanometers, the phosphorescence of the fluorescence or the scattering is very small. So it's negligible. So the dominant effect is just the absorption. So they have that. And the absorption is very big. It means that in these nanoparticles, you can concentrate a lot of energy in a small volume, and have that. If we do that, for example, this methylene blue, we did an experiment at just adding different concentrations of microspheres of latex microspheres to increase the scattering. So it doesn't affect the thermal lensing. It doesn't affect thermal lensing. It means that thermal lensing is actually in a scattering-free, technique, and I have that. There's nothing there can affect the thermal lens. The scattering cannot affect. That can have an application for some turbidity media. So they have some real media. They have a lot of things inside, and they can have some. They are turbid. They can have some turbidity, but still you can get the absorption despite that turbidity. I have that. If you do the absorbance, typical absorbance, you see big changes just because of this increased scattering, and have that. And you can actually measure the scattering quantum yield. You can see it's another spectrum. It's a little bit noisy just because we are using lamp. But if you do that with the laser, this is going to be very, very good and very easy to do. Good. Here I did an experiment with blood. That blood actually produces some differences in the thermal lensing, because blood, is a complex sample and it has a lot of scattering and so on. When you do absorbance and you compare thermal lensing, you have a big difference. But now you subtract the end, you get the scattering spectra. And you see the scattering spectra produces some different behavior and have different peaks that maybe you can use that for a different characterization of blood or other complex samples like blood. And using this thermal lensing spectroscopy. Here I did an experiment adding some milk into water. You just added milk and you increase the turbidity. You get a turbidity of 8. And this is 8 means, this is very big. It's a turbidity is E to 8. It's a very big number. You have very high turbidity. The turbidity of our skin, the human skin, is around 20. So I have this giving you the idea of if you are able to do photothermal lensing in real skin, maybe you can do some imaging. You can do some imaging similar to the photoacoustic method. And you can do imaging using the photothermal method without using X-rays and nothing like that, just visible light. This is another experiment with nanoparticles most recently. And the interesting thing about this experiment is I use nanoparticles. I bought the nanoparticles for a company called Nanocomposites. And this company provides a good set of nanoparticles, of silver nanoparticles. And at the same time, this company provides what they call a Mie calculator. So Stefan Mie was a German scientist who in 1910 published a paper about the microspheres producing a scattering of light, and he solved the Maxwell equations in details. And that paper is quite a piece of mathematical physics, but it's a very difficult paper to read and understand. And most of the people didn't pay attention to that paper because it was what they call unreadable. And I have that. But today, because of the importance of that paper, people have Mie calculators right over internet. So I just use the Mie calculator that this company provides just to compare my experiments with these predictions of the theory. So first, for example, I did two experiments. Actually, I do the absorbance experiment with a regular spectrophotometer, and I use I did the photothermal lensing spectroscopy using this Y lamp, the xenon lamp. I use the xenon lamp. And of course, when I do the absorbance, I got this complex. For example, this is an experiment done for almost 95 nanometers silver nanoparticles in water, very low concentration. And you can actually see that there are some structures, some peaks. But if you compare with the Mie predictions, with the Mie theory, the Mie model they provide by the same company, and you see more or less a good coincidence. No, there's still some differences, but you see a good coincidence between the absorbance and the prediction of the Mie theory. The prediction of the Mie theory are that dotted line that they have over there. But what interesting thing is when you do photothermal lensing, the prediction of the mean theory for the photothermal lensing is very different. It has some peak. This peak are the plasmonic peak of the nanoparticles. And they have another plasmonic peak, it's secondary plasmonic peak that actually predicted by the other people right here on around 500 and around 400 you have one plasmonic peak. But that is also predicted by the mean theory. What happens that our measurement in photothermal lensing has a very good coincidence with that mean theory, which is absolutely different from the absorbance, as you can see. And of course, if you subtract the two spectra, you get the scattering of the nanoparticle, and then I got the scattering of the nanoparticle, and I compare with the prediction of the mean theory. So the mean theory also predicted scattering, and I have that, and I will see excellent coincidence, and I have that. The paper was published about 5 years ago, and I think that after I went to Trieste, and I think I published that paper anyway. Here's another experiment we did for smaller. When you have now the scattering is less, a lot less than the thermal lensing, and you can see that it's similar. No, it has similar numbers, but you can see the comparison with the mean predictions and the measurements are really good. And I have that. That's a new way of characterizing nanoparticles. I think this is a very original way of doing a characterization of nanoparticles, because usually you can measure the transmission and the absorbance. Maybe you can measure the scattering, which is a little bit more difficult, but you can do some scattering experiments, which are not simple. But you can do the thermal lensing spectroscopy and have a good complement and compare with the predictions of an excellent theory invented more than 100 years ago. This is one interesting thing. We just measured the cross-section of the nanoparticles in total. So I have the extinction cross-section includes the scattering part and the photothermal part that here is called absorption. So the extinction has these two parts. And you see that because I have the size of the nanoparticles. I have nanoparticles that are 100 nanometers and 200 nanometers, and I can get this spectrum. I have that. Interesting thing, when you do photothermal lensing, you get this third order dependence, which is something that is proportional to the volume. It's proportional to, that's the dependence of the cross-section versus the diameter of the nanoparticle. And you see this is third order, means that is proportional to the volume. But for the scattering, it's proportional to the volume square, as predicted by the basic theory of scattering. And you can actually see that the sixth order dependence on the dimensions of the scattering grows very, very fast when you increase the dimension of your nanoparticle. That's good. We just extend that experiment using the same xenon lamp, trying to do spectroscopy on semiconductors. And I did that using, on semiconductors, you could silicon, or you can have carbon, any kind of semiconductor wafer. It's an interesting metal. You can just buy over internet, and they are polished. You need to have a good polish there for an optical applications. And then you can send a laser, an infrared laser, 1064, and that laser passes because the photons don't have enough energy for the gap. They are not absorbed by the semiconductor. And you can use that as a probe laser. And then you just use your lamp, your xenon lamp has a scatter just for doing photothermal lensing spectroscopy. And I did for the first time photothermal lensing spectroscopy on semiconductors, just using this method, and I have that. Because my time is almost over, let me go in details that we have here. In details that we obtain some places where the photothermal quantum yield is close to 1. It means that almost all energy is used for generation of heat. But in other places, it's very low. It means in other places where the photothermal quantum yield is low is where you generate some carriers in the semiconductor. So for these wavelengths, you are able to generate more carriers than for other wavelengths. That's the important thing that I think people need to characterize a particular semiconductor. This is good for solar applications, or is good for thermal or for photothermal applications. So you need to do this. You can do this kind of spectrum. For one wavelength is okay. For other wavelengths is different, the application. You can do photothermal mirror effect. That's the photothermal mirror effect. You create a bump, which is very small, and have that. And also do spectroscopy using the xenon lamp. And actually, we actually did that for a glass filter. You can do a reflection, which is nice. You know, you can actually use for any kind of sample. And then you can do for the glass filter, for the silver, you get nanoparticles just placed over a substrate of glass. And we actually obtained this spectra, which is very interesting. Still not published this data. I'm still working on that. And I see the point is that actually the spectra, the photothermal mirror spectra is very different from total reflectance. So the reflectance is you take all thing that is being reflected and you can actually see what's happening. So it means that it gives you completely different information. I have that. So we have a conclusion, right? In general conclusion, we can make a lot of different conclusions, but it is that the photothermal spectroscopy is a new kind of a spectroscopy. It's not just a simple absorption spectroscopy. It has the ability, when you combine with the absorbance spectroscopy or a scattering spectroscopy, you can define important characteristics like the quantum yield of photothermal effects, the quantum yield of scattering, the quantum yield of Raman effects, and so on. So in particular, there is an important method to characterize samples that exhibit a complex interaction with light. And I have that. And I think that the applications actually are coming, and I think the present and future applications you can do for imaging, you can do microscopy. Some people are doing photothermal microscopy. You can do reflection spectroscopy. But we are doing, you can do photothermal UV spectroscopy, photothermal near-infrared spectroscopy, and you can just keep doing different kind of applications. So people just, I think this is the first application I saw. This is the Kitamori photothermal microscope. He's a scientist from Japan, the University of Kyoto. And he was the first in the 90s to predict that you can build thermal lensing using a microscope and do some microscopic studies, and I have that. But recently I saw a company that is established in California. It's called Photothermal Spectroscopy Corporation. I think this is the first big commercial company that is using photothermal method for doing, it does the Raman and photothermal absorption in the infrared. They use the infrared diode lasers to do spectroscopy. And that is the first time I see a real commercial device that you can buy. And of course, it's very expensive because it's the first device, but these devices are common. So people are going to use photothermal spectroscopy more in the same way people have normal absorbance spectrophotometers. So we're going to have photothermal spectrophotometers in the near future, and the big corporations will pay attention to that. That's a good, interesting. You can just go to this website. They are hiring people, actually. You like that? In California, it's a nice place, and you can actually see the website is photothermal.com, and I have that. But that's what I have. All I have for today. I think my time is over.